Alright, hey everyone. So, I'm going to make a somewhat quick video about partial fractions. It's not a focal point of the test, but there's going to be at least one question where taking the Laplace will require you to do a partial fractions decomposition first. So, just as a reminder of the rules, here they are. Uh, Realistically, we don't hear what's on the top, but just hear what the factors are on the bottom. So there's really three cases we really want to be concerned about. The most basic case, when you have three different real factors, each of them gets a letter. And by the way, if you can factor more, make sure you're factored fully. Like if you had x squared minus 4, I wouldn't leave it like that. I would just factor it as x minus 2, x plus 2, and then follow the rules. So, the next case is, well, what if we have repeated factors? So in that case, you just want to put a letter over each factor counting up to the total exponent. So a over x plus 1, b over x plus 1 squared, and c over x plus 1 cubed. And if you're thinking, yeah, but why? Why does it matter? If you don't do that, one of two things will happen when you try to solve the letters. Either you'll get a system with no solution, or you'll get the letters, but it'll be a lie. You need all of these. And we do the same thing for the x plus 2 squared. Oh, oops. I'm going to throw it out there. Video editing takes a really long time. I'm not particularly good at it, and it's okay. You can put up with whatever mistakes I make and have to undo. Hopefully there won't be too many. And the other thing is, I know I'm speaking slowly, so maybe put me at 1.5. So the last case, well, what if you have quadratic with complex roots? So like x squared plus 1, I can't factor anymore. Well, for reasons I really don't want to get into, the short version is x squared plus 1 does factor as far as, well, it's x minus I, x plus I. And then that would be the first case. When you combine those, you essentially get something x plus something. And we don't need to worry about that. Right now, we know the rules. So, these are our three cases. And in general, if I have a mix of the cases, then I have a mix of the rules. So, if I had something like this, well, I would follow each rule. X plus 1 is a single and it's real, so it just gets a letter. X plus 2 is squared, so we have the one letter over x plus 2 and another letter over x plus 2 squared. And then finally, for the x squared plus 9, since it's imaginary quadratic, we have to follow that rule. I would never give something like this. Because in Calc 2 I might, just as far as saying, do you know what the expansion is? But as far as solving these, which that's the only purpose for us, we don't really care. So, but I want this to be clear, there's a mix, that's what we want to do. So, let's do a couple of examples. Here, I want to give myself more room. There we go. So, our first example, I'm just going to copy it in here. I also want to show you in a moment, in Maple, if you want to make more practice where the numbers come out nice, there's a really easy way of doing it. I know these are going to be nice. So the top looks like it might factor. Even if it did, I don't really care. We don't need to factor the top. It's the bottom I want factored completely. So we're going to end up having this just a simple piece. I do want to make a little room. We'll see why in a moment. So how do I go about solving these? I mean, admittedly, whoever you had for Calc 2, if they did it a different way, and you know how to do it that way, do it that way. Doesn't matter to me as long as it's right. There's something called the cover-up method. I have no idea how it works or how to do it, but apparently it would make your life easy. For me, I'm just making a common denominator. What is it? It's whatever this is on the left. You're essentially just putting in the missing factors. So this one's missing x, x plus 1. This is why I left the room. Alright, well now everyone's favorite way of cooking a few rotisserie chickens all at the same time. Set it and forget it. If you have no idea what I'm talking about, just look up Set It and Forget It on YouTube. You will not be disappointed. Anyway, once you have the same denominator, we can ignore the denominator. I mean, we're not really ignoring it. It's not sorcery. We're multiplying both sides of my denominator and canceling it. But let's just grab this without the denominator. So it's a lot better that way. Okay, and then, so for this, especially for this easiest case, one way we can do this without having to resort to a system of equations, we can pick x values that will make one or more factors 0 on the right. So like for instance, x equals -2, we'll cancel that out. I'll get 0 as a factor. So I'm going to let x equal -2. So on the left, that's where having editing would be great to hide my shame. So we have 4 plus 6 is 10. 10 minus 24 is -14, hopefully. We'll see. In any case, on the right, the whole purpose is everything with x plus 2 is zeroed out. So we don't really care about that. Here, these factors survive. We have -1. And again, it says x plus 2. It's just going to be 0 because of this guy. So we're left with -14 equals 2b. And so b is -7. We do the same thing. We can kill off that factor. Let x equal 0. On the left, we have 6. Thank God that's easy. Again, anything with x as a factor is going to get zeroed out. So we're left with 1 times 2. So we just have 6 equals 2c, or in other words, c is 3. And then finally, x is -1. We'll take out this factor. And so we end up getting 1 plus 6 is 7. 7 minus 12 is -5. Anything with x plus 1 is going to get zeroed out. So we're left with -1 plus 2 is 1 times -1 plus nothing plus nothing. Negative a is -5, so a is 5. Alright, and so we got our answer. If you're asking, yeah, but why do we care? Why is this important for us? Say we wanted the Laplace inverse of, I'll write this all with s's, s squared plus 12s plus 6 all over s plus 1, s plus 2, and s. Well, from what we did, I know I can expand it as, originally we had a over x plus 1, a was 5, so we have 5 over s plus 1. V we said was, well, we had b over x plus 2, so -7 over s plus 2. And then finally c is 3 over s. But now this I can take the Laplace inverse. Using our table, the first guy is like something over s minus something, so it's like e to the whatever. Well, that whatever would be -1, so -1t. Same thing for this guy. It's going to be -2t. And then finally, just the inverse of a number over s is a number. And so we have that. All right, I'll try to put bookmarks in so that way we're good if you want to see just certain examples. Jeez, come on, man. There we go. Okay, so let's do another example. So, all right, what if we have the imaginary quadratic? I will tell you on the test, for the most part, I just want the simplest case, like what we just did. But on the homework, some of them might require you to do this. So, in any case, we end up having ax plus b all over x squared plus 1. Again, leave some space. Plus, well, we just have c over x minus 1. Okay, so same thing. I want to make a common denominator. In other words, whatever that is. So what are we missing? X minus 1. Do not forget parentheses. And not just here, around the whole thing, or else it's not going to be right. Most likely, unless you just are used to it and you understand what you mean. Okay, so again, the denominator disappears. We end up having this equals ax plus b, x minus 1, c x squared plus 1. Okay, so, well, we can at least start with the same thing that we did. We want to let x equal 1 to kill this guy. So on the left side, when I plug in 1, I'm going to get 4 plus 5 minus 7, so 2. And on the right, we're going to get, well, 0, who cares, plus c times 1 plus 1 is 2. So 2c is 2. C is 1. So the main difference here is, what else are we going to plug in? We don't have anything else. I don't want to plug in I. I'm not saying it's not going to work, but it's going to be really unpleasant or good. So what I want to do is technically what we could have done from the start, just would have given us an annoying system, is write out at least what you have. Well, the 1 times that doesn't really do anything. I want to do 2 things. I want to bring this over to the other side. So we have that. And then I want to FOIL this out. So we have ax squared minus ax plus bx minus b. And we're basically going to do that same thing that we did with the undetermined coefficients. This is a common thing in math when we're setting polynomials equal, that we're going to grab what's in front of x squared, what's in front of x, and what's constant. So right away, we know a has to be 3. We also actually know negative b is negative 8. That's unfortunate looking. So b is 8. Between the b's and 8's and s's and 5's, it's enough to drive you crazy. In any case, oh good. So again, what was the point? Well, if I had to take the Laplace inverse of 4s squared plus 5s minus 7 all over s squared plus 1, s minus 1, well, I don't know that. However, if I break it up into 3s plus 8 over s squared plus 1 plus 1 over s minus 1. This I do know, and if you're thinking, yeah, but do we? Remember, anytime you have something over s squared plus a number squared, and you have both s and a number, the answer is breaking up into 2 terms. So we have 3s over s squared plus 1. We know how to deal with that. It's basically cosine. And then we have 8 over s squared plus 1. Again, basically something with sine. And now we're good. So this literally is, we don't need to fix anything, 3 cosine 1t. Plus, this guy, we have to think of what should be on the top. Remember, we have k over s squared plus k squared. Our k squared is 1, so that means k is 1. So we should have 1 up top. Well, I mean, whatever, sure we do. It's that. So we just literally get 8 sine of t, and then we have e to the 1t. And so that would be our final answer for the inverse Laplace. Okay, so last example, and then I want to show you something on Maple. So what if we have a repeated factor like that? And again, remember the inverse Laplace is very picky, so no, we don't really have a way of dealing with that, or at least not without doing partial fractions. So I can break this up as just a over x minus 2 plus b over x minus 2 squared. I will say for those of you who just skip the step and go right to not having a denominator, you're playing with fire. Don't do it. Especially not for this case. You're probably going to mess it up. It's not what you think. So again, this is our common denominator. So I'm just missing another factor of x minus 2. This guy's not missing anything. We're fine. So we end up having 4x minus 1 ax minus 2 plus b. Again, it's always worth at least trying to get one letter. So I can let x equal 2. On the left, we have 8 minus 1 is 7. On the right, we have nothing plus b, so b is 7. Awesome. Okay, so just like the last case, well, we don't have anything else to plug in, so I can just plug in what we know and distribute. I want to get rid of whatever doesn't have a letter, so I'll bring the 7 over. Minus 8. Alright, technically we have two equations. We only need one of them, and the other one just agrees. Like, we know A is 4, it has to be. And if you're thinking, yeah, but what about the other thing? Well, the other thing says negative 8 is negative 2a, which just says a is 4. No matter what, it doesn't matter. We just have superfluous equations. It doesn't change anything. And so, again, what would be the point if we had the inverse Laplace of 4s minus 1 over s minus 2 squared? Again, I don't know that, but our inverse on the inside breaks up as 4 over x minus 2, s minus 2, plus 7 over s minus 2 squared. Alright, this one isn't as straightforward. At least this guy is easy. That one we know is going to be 4e to the 2t. Fine. This one, on the other hand, we have the first translation theorem, because it's kind of like s squared, but with shifting. If it didn't have the shifting, it would just be 7 over s squared. We know that that's easy. So, since we do have the shifting, we're going to write that, which would mean big F of s is 7 over s squared. But as far as that goes, we know, like, the inverse Laplace of that would be little f of t is, well, it should be 1 factorial on the top, but 1 factorial is 1, so we're just going to get 7t, like t to the 1. So our final answer for this would be 7t, and then we have the shifting, e to the, well, a is 2, e to the 2t. And then that's our answer. This is the final answer. So, okay, how can you use Maple to make more problems? Well, here's how I knew that these were all going to work well. So, because you just make up what the actual problem is, so that way you know there's nice numbers, and just right click and hit simplify, and you're guaranteed that you can practice expanding and knowing that you got the right answer. I just stick to simple, first of all, simple numbers, and also simple factors like x plus 1, x minus 1, anything like that. And all we have to do is right click anywhere on it, simplify, simplify, and oh good, that's it, we're done. I'm also going to make a short video on just going through solving an equation on a homework using Maple so everyone knows how to do it and what's expected. But in any case, I will see you shortly, and don't forget to not mash that like button. I wouldn't bother subscribing. The other videos are either pre-algebra for other Brookdale faculty or discrete math. And either way, I don't know. I think you're good. So, I'm gonna stop recording.